Okay, good afternoon, everyone.
Good afternoon, ma'am.
Good afternoon, ma'am.
Good
Okay.
afternoon, ma'am.
Okay, so last time we were able to discuss about power. So let's now move on to our next module, which is magnetism and electromagnetism. Okay. So the nature of magnetism. Most electrical equipment depends directly or indirectly upon magnetism. So without magnetism, the electrical world we perceive today would not exist. Although there are few electrical devices used today that do not make use of magnetism. So magnets are magnificent objects. So you will really wonder why there is this attraction. Okay, so magnificent objects that create an area of magnetic force around them. So you will just wonder eventually that an object that is made of nickel iron or iron cobalt nickel is being attracted is being attracted by this magnet, although the force is invisible to human eye, but the force is there. Okay, so we call that as the magnetic field. So the natural magnets. Okay, now I made mention a while ago the magnetic objects like the nickel, the iron, the cobalt. So this objects attracts to a magnet, but non-magnetic do not get attracted to a magnet. Like for example, clothes. What else? I know that you know objects that are so-called non-magnetic. Okay, so of course the Earth behaves like a magnet. I know that you are aware of this because you have your science subject that the earth's core is believed to be a mix of iron and nickel, so giving the earth its own magnetic field. So I think that's the reason why there's this so-called correct me if I'm wrong, the gravitational pull, because the earth's core is made of this iron and nickel. So the natural magnets, the phenomenon of magnetism was discovered by the Chinese about 2637 before Christ. The magnets used in their primitive compasses were called lodestones, lodestones, or sometimes called as the leading stones. It is now known that lodestones were crude pieces of iron ore as magnetite. Since magnetite has magnetic properties in its natural state, lodestones are classified as natural magnets. Again, these lodestones are pieces of iron ore or the magnetite. Okay, so these are the natural magnets. The only other natural magnet is the Earth itself, just like what I've said. The Earth's core is made of nickel and iron. So the other magnets are called as human made, and these human made magnets are called as artificial magnets. So let's now have the next slide. So magnetic field. So every magnet has 2 points opposite to each other, which most readily attract pieces of iron. These points are called poles of magnet. So you know that I know that you are aware of the poles of the magnet, the North Pole, and then the South Pole. So just as like electric charges repel each other, okay, so like the same, when I say like, the same electrical charges repel each other, and unlike or the opposite charges attract each other. So if we are going to relate this specifically to a magnet, like poles repel, north north it repels, but north south, so opposite charges attract each other. Okay? So again, like the magnetic poles repel each other, and then like poles attract each other. So a magnet clearly attracts a bit of iron because of some force that exists around the magnet. Like what I've said a while ago, there is this force, it is just invisible to our eyes. But if we are going to place something like a paper, and then we're going to put there magnetic objects, metals, nickel, iron, cobalt, then there you will see that yes, there is really force. Because you will see now that the paper that has these magnetic objects will move as you move the magnet. But without this magnetic objects, okay, without these magnetic objects, the force is invisible to our eyes. So this force is called the magnetic field. Okay? So we call that the magnetic field. Although it is invisible to the naked eye, its force can be shown to exist by just like what I've said a while ago, sprinkling small iron filings on a sheet of glass or paper over a bar of magnet. So you will see that there will be some movement. You will see that yes, there is really force. If the sheet is stopped gently, the filings will move into a definite pattern which describes the field of force around the magnet. So the field seems to be made of lines of force that appear to leave the magnet at the North Pole, travel through the air around the magnet, and continue through the magnet to the South Pole to form a closed loop of the force, as you see now here in the figure. Okay, so the magnetic lines, that's where you will see that there is the magnetic force. And that area, that's the magnetic field, because that is where the magnetic force is. Okay, so the stronger the magnet, the greater the number of lines of force. Of course, the stronger the magnet, the greater the number of lines of force. So meaning, the stronger the magnet, then of course the force is stronger. And the larger the area covered by the field. So the stronger it is, the larger will be the magnetic area for the magnetic field. The direction of the lines outside the magnet shows the path of a north pole would follow in the field, repelled away from the north pole of the magnet and attracted to its south. So you will see now in the figure that the direction north going to the south, and then same below, north going to the south, because again, like poles repel, opposite pole attracts. Okay. Let's now have the magnetic flux. Magnetic flux. For the magnetic flux, the entire group of magnetic field lines which flow outward from the north pole of the magnet is called the magnetic flux. So again, the magnetic flux, these are the entire group of magnetic field lines which flows outward from the north pole. That's the magnetic flux. So within the magnetic field, there are lines which flow outward from north pole. Again, that is the magnetic flux. So these are the lines which flow outward from north pole. So the number of magnetic field lines passing through a surface placed in a magnetic field. That's the magnetic flux. Again, the magnetic field lines. The symbol for magnetic flux is the Greek lowercase letter phi. So that one, that it's that like a binary zero with slash. That's phi. Okay. So the system international unit of magnetic flux is the Weber. The Weber, or the WB. So 1 Weber equals 1 Weber, that is equals to 1 by 10 raised to 8 magnetic field lines. Since the Weber is a large unit for typical fields, the micro Weber, that's the micro, that's something like the U there, that's micro, and then the Weber WB, that's the symbol of the unit, is used. So 1 microweber is equal to 10 raised to the negative 6 WB. Okay? So we have here an example. If a magnetic flux, the phi, has 3,000 lines, find the number of microwevers. So convert number of lines to microweber. So we're looking for the flux. So this is just how you're going to do it. Lines over the lines per Weber. So you will see there 3,000 over the 1 Weber, which is 1 times 10 raised to the 8th power lines over WB. So that will give us, first, let us convert to the power of 10, the 3,000. So 3 times 10 cube over 10 to the 8th power is equal to 30 times 10 to negative 6 Weber. So if you are going to convert this now to microweber, this one is Weber only. So convert it to microweber, then you remove now the 10 raised to the negative 6 power, because 1 microweber is equal to 10 raised to the negative 6 Weber. Okay, now if you're going to ask me why it's negative 6 there, that is because in the law, if we are going to divide the power, then you just have to get the difference. So 3 minus 8, 3 minus 8, so that's negative 5. But since we are thinking of converting it to microweber, so what we did is instead of using 3 times 10 raised to the negative 5, we use 30. So that's why it's raised to the negative 6. Okay, so this is an example. Okay, so next is, okay, by the way, again, magnetic flux density. So, okay, so we are now here in magnetic flux density. The symbol is B. So magnetic flux density, considering a unit, there's already a unit area of the surface in which the amount of flux now, you know what are these flux? These are the magnetic lines that passes through. Okay? So the magnetic flux density now, that's the area of the surface in which the amount of flux passing through a unit area at right angles to the magnetic field lines. Again, magnetic field, that's the force for the magnetic flux. These are the magnetic field lines for the magnetic flux density. This there is already this area, unit area of surface that is involved. Okay, so the magnetic flux passing through the unit area, that's the magnetic flux density. Okay, so B, magnetic flux density, that is magnetic flux density, which is in Tesla, over area in square meters. That's the letter A. So we see that the system international unit for the magnetic flux density is Weber per square meter, or the Tesla. 1 Weber per square meter is called Tesla. So we have here an example. What is the flux density in Tesla when there exists flux of 600 microweber through an area of 0.0003 meters squared? So to find, you just have to substitute the value. So here, it's just 6. Okay, so 6 times 10 to the negative 4 Weber. So why it's just 6? That is because here, micro, we just included the two zeros. So instead of negative 6, we we included the two zeros for the conversion. So that's why it's Weber. Now, for the area, that's 3 times 10 to the negative 4. If we are going to go back how we will convert this to the power of 10, then you just have to do the same. So 1, 2, 3, 4. So that's why 3 times 10 raised to the negative 4. So that would give us 2 Tesla. Okay, magnetic materials. For the magnetic materials, are those materials which are attracted or repelled by a magnet and which can be magnetized themselves. So I already mentioned this a while ago. We have here the iron and steel are the most common magnetic materials, iron and steel. Permanent magnets are those of hard magnetic materials, such as the cobalt steel, that retain their magnetism when the magnetizing field is removed. So a temporary magnet is one that has no ability to retain a magnetized state when magnetizing field is removed. So it was mentioned here the magnetic materials. We have the permanent magnets and then we have the temporary magnets. And then we have the so-called permeability. So when we say permeability, this refers to the ability of a magnetic material to concentrate magnetic flux. Okay, so permeability refers to ability. So this is in opposite of the reluctance. So for the permeability, ability of the magnetic materials to concentrate for magnetic flux. So any material that is magnetized, easily magnetized, has high permeability. Okay? So if it can easily magnetize, then meaning the magnet has high permeability. So a measure of permeability for different materials in comparison with air or vacuum is called relative permeability. So this is the symbol. So classifying magnetic materials as either magnetic or non-magnetic is based on the strong magnetic properties of the iron. We have here the classification of magnetic materials. We have the ferromagnetic materials. So ferromagnetic materials, this include iron, steel, nickel, cobalt, and commercial alloys such as alnico and permalloy. The ferrites are non-magnetic materials that have ferromagnetic properties of iron. A ferrite is a ceramic material. The permeability of ferrites is in the range of 50 to 3,000. So a common application is a ferrite core in the coils for RF transformers. So RF, that stands for radio frequency. And then we have the paramagnetic materials. This include aluminum, platinum, manganese, and chromium. So relative permeability is slightly more than 1. And then the third classification of magnetic material is the diamagnetic materials. This include bismuth, antimony, copper, zinc, mercury, gold, and silver. Relative permeability is less than 1. Okay. So for the ferromagnetic materials, the permeability is in the range of 50 to 3,000. The paramagnetic materials, slightly more than 1. Diamagnetic materials, less than 1. Is this one clear, class?
Yes, ma'am.
Okay, this is still clear on your part. This slide. Okay, class, is this still
Yung sulat,
clear?
ma'am, hindi po, pero yung drawing okay po.
Okay naman yung drawing. Okay, so no problem
Yes
if
po,
the
ma'am.
drawing is okay. Okay. So in 1819, a Danish scientist named Orsted, okay, Orsted discovered, but no worries, class, because I'm going to give you the module for this, okay? So discovered, this is just for our discussion. So discovered a relation between magnetism and electric current. He found that an electric current flowing through a conductor produced a magnetic field around the conductor. Okay. Figure A. Can you please tell me something about the picture in figure A, this one? Okay, can you tell me something about this figure A? Okay, again, let me read the first part of the reference. In 1819, a Danish scientist named Orsted discovered a relation between magnetism and electric current. He found that an electric current flowing through a conductor produced a magnetic field around the conductor. So can you please tell me something about the figure that you see now, the figure A? Anyone? What is your observation? You just
Ako
have
po, ma'am.
okay. Who's that? Vince. Okay, Vince.
Ano po, ma'am? Um, sa akong observation po, ma'am,
Mm-hmm.
sa yung magnetic, ma'am, nagkano pa rin siya. Nagko-continue pa rin siya. But still, dun sa nilagay sa gitna, meron pa ding nabubuong magnetic field na something. Pero continue pa rin yung pag ano niya ng magnet sa kabila.
Okay, so it shows that the filings in a definite pattern of concentric rings around the conductor show the magnetic field of the current in the wire. So every section of the wire has this field of force around it in a plane perpendicular to the wire. So that's why they concluded that there is a relation between magnetism and electric current because there is a force that is being created. Okay, so you will see there is a current in the conductor because in the surface using a sheet or a cardboard with iron filings there is this movement. Okay, so for letter B figure, what can you say about the letter B figure? Okay, letter B. So there is also this ring around the conductor that shows that there is magnetic field. Okay, so it shows the strength for the letter B. For the figure B, it shows the strength of the magnetic field around the conductor carrying current depends on the current. Okay, so a high current will produce many lines of force, of course. A high current will produce many lines of force and more area for the magnetic flux, as we mentioned a while ago. extending far from the wire. So for figure C shows a low current will produce only a few lines close to the wire. Okay? So low current equals few lines which the lines that we are referring to here are the magnetic force. So high current will produce high will produce many lines of force. So that is the explanation. Okay, so here the right hand rule is a convenient way. I think you did this in your elementary. The right hand rule is a convenient way to determine the relationship between the flow of current in a conductor and the direction of the magnet lines of force around the conductor. So the thumb point and direction of current flow, that's the current, the thumb there, that's the current flow. Then the fingers score and direction, that's the magnetic field. So that's the right hand rule. Okay, electromagnet application. So here, electromagnetism, focusing on the electromagnet application. So I want you to read the statement there, and then please tell me something about the figure based on how you understand now the statement. Okay? I'm going to call or anyone who would like to volunteer. So first, read first the content. Or anyone who would like to volunteer to read the content? Anyone who would like to read the content of the slide? Anyone from the class? Hello? You just have to read.
Yung nasa taas po,
All. This one. This electromagnet application. All of the content. Please read. You want to read it, Joshua? Okay,
yan po, Ma'am
please.
Chappy.
You just have to
Thank you,
try.
ma'am.
I'll tell you if it's really if your signal is not really good. Okay.
Sige, ma'am.
Okay.
If if a bar of iron of soft steel is placed in the magnetic field of a coil, the bar will become magnetized. If the magnetic field is strong enough, the bar will drown into the coil until it approximately contained within the magnetic field. Electromagnet pati ba?
Yes, yes.
Electromagnets are widely used electrical devices. One of the simplest and most common applications is really when the switch is closed in relay circuit. Current flows in the coil, causing a strong magnetic field around the coil. The soft iron bar in the lamp circuit is attracted towards the right end of the electromagnet and makes the contact with the conductor at A. A path is thus completed for the current in the lamp circuit. When the switch is open, the current flow through the electromagnet ceases and magnetic field collapses and disappears. Since the attraction for the soft iron bar by the electromagnet no longer exists, the iron bar is pulled away from the contact by the piece of spring steel to which it is attached. This opens the contacts at A and breaks the circuit for the lamp.
Okay. So anyone who would like to share their insight with regards to this magnet application? Anyone? Anyone, class? Can you can you please tell me something about the figure, the simple relay circuit? Anyone? Anyone who would like to share? What can you say about the figure based on the readings of electromagnet application? No idea. So actually, what we are just going to put emphasis here is that when the switch is closed, okay, when the switch is closed in a relay circuit, current flows in the coil, causing a strong magnetic field around the coil. Okay? So again, when the switch is closed in a relay circuit, there is it leads to a strong magnetic field around the coil. Okay? When the switch is opened, when it's open, the current flow through the electromagnet ceases. So it stops. Okay, if it is open, when the circuit is open and when the circuit is closed. So that's why if this closed circuit, then for sure it will cause for a strong magnetic field. But when the circuit is opened or there's break, then it will cease. Okay? It will cease, it will disappear, it will break the force. Okay, so what this is just what this slide is trying to tell us. So let's now go to the next slide. Next slide. So where are we now? So here, magnetic units. So magnetic units magnetic units ampere turns, and that's the ampere turns. So the strength of a magnetic field in a coil of wire depends on how much current flows in the turns of the coil. The more the current, the stronger the magnetic field. The more there is this the more the larger number of the turns, of course, the more the current, the stronger the magnetic field. Also, the more turns, the more concentrated are the lines of force. So this is just what I just said a while ago. The product of the current times the number of turns of the coil, which is expressed in units called ampere turns, is known as the magnetomotive force. So magnetomotive force, or the MMF. Again, magnetomotive force, or the MMF. So F is equal to ampere turns, that's equal to Ni. Ni, that's the ampere turns. F, again, that's the magnetomotive force. That's the AT, the unit is AT. Then N, that's the number of turns. So what did we say about the number of turns? The more the turn, the more concentrated are the lines of force. And then the I there, of course, that's the current, and then the unit is ampere. So we have here an example. If we want to calculate the ampere turns for a coil with 1,500 turns and a 4 milliampere current, so we use the equation F equals Ni. So we just have to multiply it. So N there, it's not 150. It's not 150, but it's 1,500 turns. Okay, so it's not 150, but rather it's 1,500 turns. So we just have to multiply it and we will arrive at that answer. Okay. So it's just very simple because anyway, the given is there, then you will just see the formula exactly as it is, as what you have seen it. Okay, so field intensity, if a coil with a certain number of ampere turns is stretched out to twice its original length, the intensity of the magnetic field, that is the concentration of lines of force, will be half as great. Of course, the field intensity thus depends on how long the coil is. So expressed as an equation H, that's the magnetic field intensity H, then N, that's the number of turns, Ni, number of turns, then I, the length between poles of the coil. So again, for the magnetic field intensity, that's H equals Ni over L. Ni, that's the number of turns, and then over the length between poles of the coil. So here is an example. So you will see here in the example. Is this clear in your end class?
Clear po, ma'am.
Okay. Anyway, in the modules,
Malabo po.
okay, it's not clear. So anyway, we'll just have to. But okay, for a while. Let me check my module. Okay, let me check my module. So where are we now? Okay, so we are here now in magnetic field intensity. Magnetic field intensity. Okay, so find the field intensity of a 40 turn, 10 centimeter long coil with 3 ampere flowing it. So we'll just have to, so we will just have to, for a while. Okay, so we'll just have to follow the given formula, which is H is equal to Ni over L. So that will give us 40, that 40 number of turns will just be multiplied to 3 amperes. Okay, 40 times 3 divided by 0.1, because 0.1, that's the equivalent, that's the converted value of 10 centimeter, this 10 centimeter to meter. So we will have, the answer will be 1,200 because of 40 times 3 divided by zero point 0.1. Again, where did we get the zero point 0.1 converted centimeter to meter? Okay, so same with number 2 and number 3. You just have to follow the H is equal to Ni over L. Okay, let's have the magnetic units. Magnetic units, a magnetic circuit can be compared with an electric current in which an electromotive force produces a current flow. The ampere turns of the magnetomotive force produce the magnetic flux. Therefore, the magnetomotive force compares to electromotive force or voltage, and the flux compares to current. So opposition to the production of flux in a material is called the reluctance, which corresponds to resistance. So this is opposite of the permeability because reluctance is like the resistance. Inversely proportional to permeability. So that's just like what I said a while ago. Okay? So different forms of electromagnets generally have different values of reluctance as shown in the figure below. So take note of this. The air gap is the air space between the poles of a magnet. Since air has high reluctance, meaning the size of the air gap affects the value of the reluctance. The magnetic circuit, as shown in the figure, later you will see, has widely spaced poles. So you will see, okay, I think it's better for me if you are going to see the, or wait, okay, this one. Wait for a while. Okay, here, so the air gap, again, like what I've said a while ago, the air gap is the air space between the poles of the magnet. Okay? Since the air gap, the air has high reluctance. So again, when we say reluctance, opposition of the magnetic flux. So the size of the air gap affects the value of reluctance. So figure A, you will see this one, figure A, the magnetic circuit as shown in this figure has widely spaced poles in air. So widely spaced poles. So there is more air gaps. So meaning more air gaps. So it has high reluctance. So for B figure, the reluctance has been decreased by bringing the two poles closer together. So you will see there the North Pole and then the South Pole. The field between these poles is more intense. So that is why the reluctance is lower. Unlike in letter A, in figure letter A, there is this high reluctance because because of the widely spaced poles in the air. So for figure C, the air gap is smaller. Okay, so therefore, still the reluctance is lower. But in letter D, there is this lowest reluctance because there is no air gap in this toroid shaped core. So that is why the letter D there has the lowest reluctance. So take note, the shorter the air gap, the stronger the field in the gap. Since air again is not magnetic and thus it's unable to concentrate magnetic lines. So a larger air gap only provides more space for the magnetic lines to spread out. Okay. So now, okay, so you just have to hear the Ohm's law, the application of Ohm's law to a magnetic circuit. So this one is the magnetic flux, the phi, mmf, the magnetomotive force, r, the reluctance. So reluctance is the length of coil over the permeability across for the cross times the cross sectional area of the coil. So let's skip to this. These are just formula. Okay, so here I want you to I'm going to ask the class what is your insight in this module 5. Let's have the electromagnetic induction. So this one is just I'm not going to discuss this anymore because everything is there. This is a step by step. This is this one just want to show just asking to show why we have this equation or reluctance to this length over this number of this permeability and then this ampere. Okay, permeability, not ampere, but rather the cross-sectional area. Okay, then you just have to do the substitution. So like for example, here B, what's B? That's also this one. It's this permeability, then this H, the intensity. So substitution, you will just be doing the substitution just like what you do in math, the substitution. So that's why we have this reluctance is equal to length over the permeability times the cross the area. Okay, now here I'm for the electromagnetic induction. Okay, I want you to read this electromagnetic induction and I'm going to ask the class what is your reflection. So anyone, please read The Electromagnetic Induction by Michael Faraday. Anyone?
Ako po, ma'am.
Okay, Vince.
In 1831, Michael Faraday discovered the principle of electronic induction. It states that if a conductor cuts across lines of magnetic force, or if lines of force cut across conductor, an amp or voltage is induced across the end of the conductor, shown in the figure below. The conductor C, which can be moved between the poles, huh? His conductor is not moving. The galvanometer shows 0 F. If the wire conductor is moving outside the magnetic field at position 2, it cuts across the lines of magnetic force and the galvanometer pointer will deflect 2.
Mm-hmm.
This indicates that
Okay, just continue.
an EMS was induced in wait naman mawawala. This indicates that an EMS was induced in the conductor because lines of force were cut. In position 3, the galvanometer pointer of the conductor by moving it right through the line of the force back to position 1. During this movement, the pointer will deflect to B, showing that an EMS has again been induced in the wire. But in the opposite direction, if the wire is held stationary in the middle of the field of force at position 2, the galvanometer reads 0. If the conductor is moved up or down parallel to the lines of force so that none is cut, no EMS will be induced.
Okay. Okay, let me show you this one. Okay, for a while. Start new whiteboard. Okay. Okay, can you see my whiteboard? Not yet.
Wala pa, ma'am.
Okay.
Wala pa po.
Okay, this how about this one? Can you see the whiteboard?
Yes,
Yes
ma'am.
po.
Okay.
Yes po, ma'am.
Okay. So
Yes po, ma'am.
here I'm going to draw. Okay. So I'm going to draw a galvanometer, something like this. Galvanometer. Okay. This is a galvanometer. Then it's letter G because this is a galvanometer. And then this is 0, for example, 10, 20, okay, another 10, 20, then there is a needle. There is a needle. And then this galvanometer is connected to a coil of wire. Yeah, the coil of wire. Coil of wire, which, okay, example like this. Okay, this is the coil of wire connected here, here. Okay. And then we have imagine this is the Faraday's law, okay? So this is the Faraday's law. This is the Faraday's law. Oh,
Paradise law.
okay, this is the Faraday's law. Okay, so for example, I have here a magnet, and you know that there are two poles. For example,
South and
south, yes, the south and then the north. For example, the north is the one facing down. Okay, the north is the one facing down. So again, you imagine there's a galvanometer, there is this coil of wire, there is a magnet. So, question, what will happen to the needle of the galvanometer when you move in the magnet to the coil of wire? What will happen to the galvanometer when you move the magnet inside
what
the
will
coil of
happen
wire?
will the diameter when you move.
Yes, what will happen? What will happen to the galvanometer, to the needle of the galvanometer? When you move, when you move down the magnet, what will happen? What do you think will happen? Okay, what will happen? There will be what? There will be when you move. Example, I'm going to move this. The North Pole is the one facing down. Okay, I'm going to move the magnet inside the coil of wire. What will happen now to the galvanometer? What will happen to the galvanometer? There will be what? Anyone? There will be what?
Electromagnetic induction po.
Okay, there will be, what do you think, class? There will be deflection of the needle. So meaning the needle will move. Okay? Once I move inside, once I move inside the magnet to the coil of wire, then the reaction of the galvanometer is there will be deflection of the needle. Now, the next question is, since the North Pole is the one facing down, what will be the direction of the deflection? Going to the left or going to the right? Going to the right or going to the left? As you put down the magnet inside, it will be going to the the deflection will be going to the right. Okay, again, once I move inside the magnet in which the North Pole is facing down, then there will be deflection and the movement will be going to the right. But as I move up, going away from the coil of wire, what will be the deflection? It will be going to the left. Okay, there will be again movement going to the left. So, how about if you put stationary the magnet inside? It's not moving, it's just stationary. Will there will be movement? Yes or no? For example, I move inside the magnet, and then inside the magnet now is stationary. The question is, will there will be movement of the, or there will be deflection in the galvanometer? The answer is no. Meaning, if the magnet is stationary, there will be no deflection. Okay? Now, let us now change the position of the magnet. So instead of N facing down, it will be the south pole. Okay? When you move inside the magnet in which the south pole is the one facing down, there will be an opposite deflection. So instead of going to the once you put inside this, instead of going to the right, it will be going to the left. But once you move it out, then instead of going to the left, it will be going to the right. But still, regardless of the position of the poles, if it is stationary, then there will be no deflection of the needle. So meaning if it's just active, then that is the time that there will be this movement or deflection of the needle. Okay? Is it clear now, class? Okay, clear. Is the explanation of the galvanometer and the coil of wire and then the magnet is clear, class?
Yes, ma'am.
Okay.
Po, ma'am.
So let's now have the last one. So the last is, so here you will see, let me share screen again. So where is it now? Okay, for a while. Okay, where is it? Okay, let's see. Module 5. Okay, so when lines of force are cut by conductor, or lines of force cut a conductor, an EMF or voltage is induced in the conductor, there must be relative motion between the conductor and the lines of force in order to induce an EMF, or the electromotive force. Changing the direction of the cutting will change the direction of the induced EMF. The most important application of relative motion between conductor and magnetic field is made in electric generators. In a DC generator, fixed electromagnets are arranged in cylindrical housings. So many conductors in the form of a coil are rotated on a core within the magnetic field, so that these conductors are continually cutting the lines of force. As a result, voltage is induced in each of the conductors. So since the conductors are in a series in the coil, the induced voltage add together to produce the output voltage of the generator. Okay, so the last one, that's the Lenz's law. Okay. For the Lenz's law, for the Lenz's law, so you just have to imagine holding a magnet in which the north pole is pointing towards the coil of wire. The question is, what will happen when you push in the magnet going to the coil of wire? What will happen? Imagine you're holding a magnet. Okay, so imagine you're holding a magnet. Okay, you're holding a magnet in which the north pole is pointing towards the coil of wire. So there is a magnet in which the north pole is facing towards the coil of wire. Then the question is, what will happen when you push the magnet going to the coil of wire? It will, the coil of wire will push away the magnet. But as you move away the magnet, the coil of wire will attract the magnet to get closer. So that is the Lenz's law. Okay, by the use of Lenz's law, the left end of the coil must be the north pole to oppose the motion of the magnet. Then the direction of the induced current can be determined by the right hand tool. If the right thumb points to the left, for the end pole, the fingers coil around the direction of current as shown in the figure. So where's the figure? Okay, so that is just what you are going to remember. Okay, so there is you're holding a magnet. Then there is this coil of wire. As you move the magnet towards the coil of wire, the reaction now of the coil of wire is to move away the magnet. But as you move away the magnet, the reaction of the coil of wire is to attract the magnet to get nearer. But as it get nearer, it pushes away the magnet. So that is the Lenz's law. Okay, now class, I have I have posted two activities in your Google Classroom. One activity is the exercise for module 4, and then the other activity is for today's session. Okay? So since it's already 4:47, I just want you anyway, the deadline is, I can change the deadline because supposedly I should have dismissed the class earlier, 4:30, but since it's already 4:47, I was not able to manage my time. So I will just have to change the deadline of the two activities that I posted earlier. Have you checked your Google Classroom, class? Not yet.
Not yet po.
Okay.
Wala pa po, ma'am.
So anyway, I will just have, like what I've said, I will just have to change the deadline. But please check your Google Classroom because like what I've said, there are two activities posted. One is exercise for module 4, then the other one is for module 5. Okay, so please write your name in the chat box for your attendance today. Okay, please write your name. Perhaps I'm going to announce maybe next meeting when will be your midterm. So you just have to always check the updates. Okay, so again, class, be productive. You still have 10 minutes, 10 minutes, yeah, 10 minutes pa to. 10 minutes to check your Google Classroom. Then no worries because like what I've said, since I was not able to manage my time sched. Like what I've said, possibly 4:30 will end at 4:30. I was not able to make it. So I will just adjust the deadline. Okay? So that's all for today about magnetism and electromagnetism. So I hope you learned something from today's session. So again, check your Google Classroom. Okay? So that's all for today. Bye.
Hey, ma'am. Thank you.
Thank
Okay.
you, ma'am.
Thank you, ma'am.